Welcome everybody to the Good Data Podcast. Today is episode 3 of our Green series. Last week we had a great interview with Daniel Pope about immersion cooling, and the week before that we jumped right in with green software. We started there because it really is the most important piece of the movement to save electricity and computation. Poorly optimized software literally wastes billions of dollars and terawatt hours of electricity every year. So this week we're zooming out just one level from the software layer to the physical layer. This episode is all about green hardware, servers, networks, and racks. This may sound crazy, but it's true. The next biggest savings still isn't cooling or power systems or anything to do with the large-scale data center systems. Server hardware really has the biggest impact next to software. So today we're going to talk about some hardware trends that I would love to see continue. These are things that can be utilized right now, this very day, in your facility. Let's go! This week, I think, will be a barrage of information regarding server and hardware design. I'll be frank here, this is not my main area of expertise. I consulted with a lot of people, but I have my biases, so I'll probably miss something here. If you want something to be brought up in a future episode, email us at gooddatapodcast@gmail.com. First off, let's answer this question. Why is server hardware and design so important? We already established that saving 1 watt of power at the CPU saves up to like 2.8 watts in total. That's because 1 extra watt from the CPU requires extra energy from the power supply, which requires extra energy from the UPS, and the UPS loses about 3%. So all of that makes heat, which requires extra energy to cool down. So we're starting as close to the chip as possible to minimize all those losses and then moving outward. We talked about software, what happens inside the CPU last time. Now we're going to talk about server hardware, by which I mean everything between the processor and the electrical outlet. I'm going to use some of the framework from the Open Compute project because I like Open Compute. I believe in it. I think they're doing some really good things, but I also like that you can see the thought process behind it and how the group is trying to tackle some very complicated issues. Now, Open Compute is really geared toward the boots on the ground, like the server manufacturers. Most people don't need to know this stuff. Also, non-Open Compute manufacturers have really cleaned up their game and done some great work to improve efficiency. So it's not just the Open Compute. This really does apply to everybody. But I'm going to be talking a lot about Open Compute just because it's well documented, well organized, and it's pretty damn comprehensive. If you're interested, go to opencompute.org. Okay, so what's the first part of the computer that we can improve?
Processor efficiency.
All right, so we said we were starting as close to the chip as possible, and here we are at the chip, the actual computation of computing. So most people think of the CPU as the computing chip. That's what you think of when you hear, all the way back to the days of the 486 or the Intel chips, anything that's based on an x86 architecture. But that's changing because we have a lot more application-specific types of computation these days. So one of the first big breakthroughs in that was GPUs, graphical processing units. People started to realize that these things did floating point computations really fast because that's what's required for graphics processing. But those floating point computations can do a lot of other stuff like computational fluid dynamics or other types of modeling, genetic research. So taking that architecture and using it for other stuff became a natural process. And so that has really improved the computation per watt for those types of computation. But also, there's opportunity there for even more specialized chips for different types of computation. So I talked about genetic analysis, or let's say chemical analysis. There are chips that are specifically designed to do that. And when we talk about specifically designed chips, one of the best ways to think of it is a chip that is for a single purpose. And where this is really blown up is with Bitcoin or cryptocurrency mining. There are chips that all they do is mine cryptocurrency. So they're just doing that one very specific hash algorithm over and over and over again as fast as is possible. And they've gotten really good at it. They can do in 1 second a trillion or a tera hash, when before a lot of computers can only do 100 hashes in a second. So these things have gotten a whole lot better at doing the thing that they're supposed to do. So when you get those application-specific integrated circuits, or ASICs, you can do processing an order of magnitude faster for less energy. And as we start to develop more and more ASICs, we start to be able to improve by orders of magnitude the efficiency with which we do computation. So that's part of the reason that the cloud is actually a really good thing for computation, is that those cloud companies have enough money to spend on developing these ASICs for their particular application. And that means that they can do the same actual processing as you would do at home, but they can do it for 1/100th or better sometimes of the processor power. So it's becoming more and more that complex computational tasks really shouldn't be done from an energy perspective on your home computer or your work computer. They should be done in the cloud. It saves a lot of money and a lot of energy. And hopefully that's only going to get better. Okay, what's the next thing we can improve?
Memory buses.
So this is related to the chip, but it's sort of the next level up. The memory bus is actually a lot of times located on the chip, but there are a lot of new architectures that actually combine additional cores in the same silicon, so they can share that level 1, level 2, and level 3 cache, which means that they can get some economies of scale. And if they're communicating with each other, if there are different processors in the same silicon, sort of like the GPU setup, they can share information ultra fast between them at extremely low energy. So increasing the die sizes of chips can actually be a really good thing for computation. And AMD has been one of the forefront leaders in this with their Threadripper CPUs, which have, I think it's 48 cores on a single chip, and they can do things similarly to a GPU, but each one of those cores is actually a little stronger than the GPU cores in a graphics card. So by putting everything on the silicon, it can simplify production, but it can also reduce the actual energy use. And another big change in that is the SoC, the system on a chip, where you actually have almost every function that is required for computation within the bed of silicon. You can even have things like Wi-Fi connectivity or Bluetooth that are inside of a chip, which really saves on the electrical usage. So as these things get better, they're going to improve the total amount of, or they're going to improve the watts per unit computation. All right, next.
Disposal.
Okay, so far we've been mostly talking about the energy usage and how that's a green technology for data centers. But this one specifically is not a green issue. This disposal is one of the few times that we're talking about actual environmental damage from pollution, basically. Data centers themselves don't really pollute, but all of the hard drives that are thrown away, all of the server hardware that's thrown away, all of the cabling that's thrown away, a lot of that ends up in landfills, or hopefully it's put into an e-waste facility and disposed of properly. But there's a lot of really awful byproducts of PCBs, printed circuit boards, and silicon chips, and all the different components of a computer that really need to be disposed of properly and that really can have harmful effects on the environment. So it's really important to have a reputable and certified disposal company. And they're around. They cost a little bit more, but really you should be using them anyway because it's good for business, because you need to make sure that you properly erase all the data on your hard drives, and just writing it over a million times may not be good enough for certain types of data. So you need to have a proper disposal company that is NAID certified to make sure that that data actually gets erased. So I said NAID, there's other certifications that are really worth looking into for disposal for e-waste. One is e-stewards, which is sort of an environmental concern. Another one is the R2 certification. Another one is ISO 14001, which has to do with just green processes in general. And then I think this is an interesting one, but I think it's a good one. A lot of these materials are actually very hazardous for human health. So I think that it's important to also have a certification for occupational health. So one of those is OHSAS 18001. And it's worth just checking up on your e-disposal companies and making sure that they have those.
Right to repair.
One last caveat to all this is something that is very important, I think, in this day and age, and that is supporting right to repair. So I could get on my soapbox for about a day and a half just talking about right to repair, but at this point, a lot of hardware is actually not available for repair because of the law, the Digital Millennium Copyright Act, which says that anything that has a software lock, like rights management on it, you're actually not allowed to repair that device. It's against the law, but you own the device, so it's almost like taking your ownership of this device away from you by saying that it's illegal. And I understand the reasoning for it is that we want to have software licenses that incentivize software manufacturers to create software. And so they put digital rights management on in order to safeguard their software. Problem with that is we should still be able to repair the hardware. It's just an example of this is, I don't want to make any enemies, but John Deere has put rights management software on their tractors. And so it's illegal for anybody but a John Deere technician to do work on those tractors. But there's a ton of farmers in the field who, when their stuff breaks down, they can't wait for a John Deere technician. So they're breaking the law just by doing their jobs. And I really think that's got to change. But before I go any further, let's just go on to the next question.
PCB optimization.
So this is similar to that system on a chip, but the more that you can reduce the total area of a printed circuit board, the less energy it takes, because every centimeter of copper that energy has to go to has a certain amount of resistance. So by reducing that distance, you're actually saving energy. And part of the reason that circuit boards are the size that they are and the distances apart that they are is because of heat. So if we can dissipate that heat better, then the circuit boards could actually get smaller and denser. So anything that we can do to improve heat dissipation is actually a really good thing for the entire system. More on that later. Next question.
Blades, blocks and hyperconverged fabrics.
So I bet a lot of you haven't really thought of blades too much recently. Blades, blocks, microblades, hyperconverged fabrics. There are all these different names for basically taking compute resources and making them in smaller chunks and then plugging those into some kind of shared backbone that has the networking and power inside of that, so that you don't have that overhead every time of having the networking and power for each server. So it's almost like making these little microservers. And that trend has helped a lot. A lot of times it ends up being this hyper-converged solution, but also Open Compute does this. And the ability to break the computation into smaller pieces than just what you think of when you think of a 1U pizza box server. So by doing this, it actually does create a lot of efficiencies, because that larger power supply can be more efficient, because you're getting things closer together, like I was saying. So every centimeter of copper is actually shorter, so there's less resistance, you're wasting less energy. And these things have changed a lot. They've gotten closer together, they've gotten smaller. I think that the majority of server hardware in the future is going to be like this. It's interchangeable. I would love to see this continue, but we'll just have to see how it goes. Next.
Monitoring.
This is a complicated one because there are a lot of things that you can monitor from a server. You can get SNMP data that gives you a lot of different outputs. You can figure out if there's a fan problem or some other issue. But very little of that is actually pulled back into your building management system or anything that looks at the total amount of energy in the data center. But there's an opportunity there that I have never seen taken up, which is actually to look at the chip temperatures and to modulate heating and cooling based on the chip temperatures, because that's really the thing that you're most worried about. It's not so much that the inlet temperature of a given server has to be a certain amount. It's that the actual temperature at the chip has to be a certain amount. So if we were to take the maximum allowable temperature of a given chip and subtract, 10%, then use that to control our thermostats, that's actually almost definitely a higher number than the rack inlet temperature tells us. And it's also a much more helpful number, and it's a more accurate number. And some of those should be available. If they're not, but they should be available on SNMP and should be broadcast. And it would be fantastic if we could take that information from the circuit board and pull that into a building management system. I don't know if that's ever going to happen, but man, it should.
Labeling.
Okay, so labeling. This is just a pet peeve of mine. Everything is more efficient when it's labeled, when you know what it is, when it's accurate to what the device is, when you're delivering a service and connecting it to an actual physical piece. You should know what physical piece that is. And part of that does come down to labeling. And whether it's QR codes or barcodes or some other machine readable or non-machine readable piece, everything really should have a label. Next.
Efficient power supplies.
Power supplies are interesting because they are taking AC power and converting it to DC. The problem with that is that in a data center, it has already been converted to it's AC power comes into the facility, it gets converted to DC at the UPS batteries, then it gets converted back into AC coming out of the UPS, and then it goes into the power supply and gets converted back into DC. That's a lot of conversion steps. And if you could increase the efficiency along any part of that chain, it makes a huge difference. Also, converting everything to DC really can help with some of those conversion steps and make the whole thing more efficient. This has gotten a lot better over the years. UPS efficiency has improved, and so has the power supply efficiency, but it's still a problem. Now, places like Facebook and Open Compute have decided that they could use 277 volt AC input for their power supplies. And that's interesting because the higher voltage, the less that there's losses on the AC side of the equation. And the longer your cable runs can be, the smaller the wire. So there's savings there. But there's also an awful lot of savings in putting DC power as close to your rack as possible and eliminating a lot of that AC conversion to DC to AC, whatever it is. Next.
Efficient fans.
So fans. Fans are an integral part of cooling. And in many servers, they are simple brushless fans, and they're very efficient. They've gotten a lot better. But fan placement and the motion of air is incredibly important in server design. And replacing your fans and making sure that those fans are actually operating properly can really improve your equipment life. So monitoring your SNMP points and making sure that you know if there's a busted fan is really worth looking at. We have to take a break. We'll be back in a moment on Good Data. Today's episode is brought to you by Greenlane Design. Greenlane is a full-stack design, bid, build company focusing on data centers. They've developed projects from BOD to finished turnkey build for many different types of companies, including colocation, high density, and enterprise. If you would like to get a free assessment, go to greenlanedesign.com, click on Contact, and mention the podcast. And we're back.
Eliminate 120 volts UPS.
Okay, so here's another little soapbox about small data centers or anything that really operates on a 120 volt feed. The problem with a 120 volt feed is that a UPS that's built on 120 volts is inherently less efficient by a whole lot than something that is built on a 480 volt or 208 volt three-phase topology. So in electricity, everything is based on waveforms. So there's single phase, which is what you have in your house, where you have a 60 hertz wave. And then there's three phase, which is what you have in an industrial facility or a data center, which has three different 60 hertz waves that are offset. Mathematically, not to get too hung up on this, but mathematically, those three waves should always balance out to zero, that they're always offset in such a way that they're exactly 120 degrees off, so they balance out, and there's no residual current on that, which means that UPSs love that because they don't have to do any of that balancing on the back end to condition that power. They still do a little bit, but they have to do so much less than on a 120 volt system. A 120 volt, the most simple derivation of a 120 volt AC to DC power is through a bridge rectifier. And that creates this, I'll say, a bumpy DC. It's not a perfect DC flatline voltage. So what they have to do is they have to put in conditioners for that power, which are basically capacitors that then smooth out that bumpy DC, which all of that costs power. It's not efficient. So that's why bigger data centers are always inherently more efficient than 120 volt power supplies and 120 volt UPSs. I hate to see 120 volt UPSs. It's just a waste. So anytime that those things can be put inside a data center, it's saving energy and making things more efficient.
Bus racks.
So what we mean when we say bus racks is actually putting electrical copper connections in the back of the rack so that you don't have to have PDUs or plugs or anything. It just, the server plugs right into bus, which is just a piece of electrical copper in this case, in the back of the rack. And that's one of the open compute standards. I like it because it simplifies deployment. You don't have to worry about cords or cord management, which is a huge pain. So being able to just have the bus in the back means that you can just take the server and plug it right in, and you don't have as many problems. That goes into our next one. Let's talk about that.
48-volt DC power shelf.
So this is another open compute standard, and the great thing about it is that it's a 48-volt DC power connection. So like we were saying before, you are not converting that AC to DC, back to AC, back to DC. You're just going AC to DC and staying there at 48 volts and then plugging that directly into the server. So the reason that that saves money not only is the lack of that transition, but also it's just saving complexity. You're just plugging into the back, and then these power shelves actually are integrated so that you don't have to worry about any of that cabling. You can modularize your deployment very easily. Next.
Improved temperature and humidity envelope.
So, data center heat envelopes. Okay, so the temperature at which the air can flow into a server is, usually in the United States at least, we use the ASHRAE recommendations. And the ones that I like to use are from TC 9.9, which state that the incoming temperature has to be between 64.4 degrees Fahrenheit and 80.9 degrees Fahrenheit. It opens up the envelope for what is allowable inlet temperatures for servers so that you don't have to put your cooling on this really, really fine range so that it's always in cooling or always dehumidifying or always adding humidity. Because adding humidity takes up a lot of electricity, so does dehumidifying. Actually, dehumidifying takes up an enormous amount of electricity. So if you never have to dehumidify, you're saving an astounding amount of electricity. So by making servers able to handle, let's say, 10% to 90% relative humidity, and let's say, if you were to say 32 degrees to 100 degrees Fahrenheit of inlet temperature, you could save so much energy by not having to air condition ever, or almost ever. And some computers can actually handle that range, but they have to be rated for that, or else you're voiding your warranty by extending beyond that range. So it's a real issue that that server manufacturers have to be comfortable with staying within wider ranges. And there have been some studies, Intel did one a few years ago, that showed just simply outside air without much filtering really didn't decrease the life of their servers very much. It was an experiment, and it worked pretty well. I think it was about 3% increase in the number of failures, which is legitimate and is something to think about, but it's not that bad, and maybe saving the electricity is better than losing the equipment. I don't know. It's really a calculus that people have to do on their own. But if the servers can handle a wider range, it just helps. Next.
Airflow optimization.
Okay, so CFD, computational fluid dynamics, in this case is optimizing the airflow inside of the server itself. So most servers that you get these days actually have gone through a CFD analysis to make sure that you get optimal airflow to the chip and and actually everywhere that needs to be cooled within the server. You can kind of see where the airflow goes inside of a box just by, if you have an old server, one that's been around for 5 years or so, open it up and look where the dust went. You can see almost, exactly, the the airflow went through this heatsink right here. You can tell where the airflow was and how maybe to optimize it in the future. Ideally, the airflow should go directly through the processor heatsink if possible. It should go front to back so that air isn't recirculating within the server. There should be careful management to make sure that that hot air from the CPU doesn't go into another critical component. It just goes flowing out the back. So that brings us to our next one.
Air quality and filtering.
So, because of the dust that is in the air and the problems that that has for server airflow, that's why it's important that data centers be clean rooms, because it's not the only reason, but having particulates in the air or dust actually impedes the airflow through the fans of the servers. And it gets stuck on heat sinks, it gets stuck all through the server components, and it just makes the whole thing operate less efficiently. So it might not seem like a big deal, but even just pollen in the air and outside air infiltration, these things actually have an effect on the heating and cooling of your data center and the chip temperatures and everything that we've just been talking about. So having good filtration in a data center is worth something. And also, having particulates in the air can cause zinc whiskers and can short out electrical components and can reduce the life of hardware. And so it really does make sense to have great air filtration, and the best data centers do. Next.
High quality heat sinks, heat pipes and vapor chambers.
Okay, so this is an interesting one for me. Heat sinks, vapor chambers, heat pipes, these are different ways to get heat away from the chip. A heat sink is just a slab of metal, usually copper, that conducts the conducts the heat away from the chip and puts it through fins that then air goes through and cools it down. Heat pipes are similar. A lot of times they're attached to a heat sink, but what they do is they actually have a compound inside them. I'll just say compound. It's sort of like what you would have in an air conditioner, that it evaporates at a certain temperature when it's close to the chip, and it takes all that energy from evaporation and takes it away from the chip, and then it goes through the heatsink, and inside the heatsink, it dissipates all that heat and turns back into a liquid and then drips back down onto the chip. And by doing so, it takes a lot of energy very efficiently in a small space. And that is a requirement for very small space work. So most laptops have heat pipes in them. And when you open up a laptop, you'll see like a flat piece of copper that is going across it. And that is what that's doing. It's running a liquid gas mixture, or a liquid that turns to gas, to a heat sink that is getting rid of that heat. And they can be very efficient, but they have to be designed properly. So one of the ways that they change that is a vapor chamber, which is just like a heat pipe, but it's actually sort of flat against the chip
Unified
itself.
power
So it just has
supplies.
more contact area with the chip, and so it's a little bit more efficient. Either way, it's just optimal design and having good framework and heat design within a server. So that's why part of the reason that you want to go with a reputable server manufacturer and not some fly-by-night organization is that these things are done properly in those types of systems.
Liquid cooling.
So we talked about vapor chambers and heat pipes, but in reality, there's almost nothing better than water. Water is a very, very good heat conducting material. It can take, I forget what the actual heat density of water is, but water can carry a lot of heat within it and per unit volume. So you don't need that much water to do all the heat rejection that you need. The problem is that you have to get that water someplace. So you have to run it through some kind of a heat rejection system. And the other scary part about water is that it's conductive. Because of the ions that are in the water, it can short out electricity. It can short out electrical systems. If you were to use deionized water, that would be okay, but DI water is hard to produce. It can be corrosive. I think I've heard varying accounts on that, and I wish I knew better. Because I know that they use DI water to cool systems in nuclear power plants and a lot of places, but I've never seen it used in a data center, and I'm not sure why. I think it might be because of the threat of infiltration within the ions that are within the electrical components. I'm not sure. But using water to run through pipes that are within the server is one of the ways that a lot of the best supercomputers work. And the great thing about that is that it makes the heat rejection as close to the chip as possible with as few steps as possible. So a lot of systems out there in the world have some sort of water as part of their heat rejection, whether it's a glycol loop through a dry cooler or a cooling tower that evaporates water, or whatever different type of water-based cooling system there is. They use water because it's such a good conductor of heat. So by getting that as close to the chip as possible, you're taking that heat conduction capacity and getting it so close to the chip that it actually can improve the efficiency of the entire system. Problem is, it's a lot of piping. It's a lot of stuff to maintain. It's complicated. It's expensive. And most of the time, it's not worth it. It's just too much. It's overkill for most types of applications. So that brings us to our next topic.
Rack door cooling.
So I'm including here rack door cooling because at the outset of this, I said that we were going to talk about all the components from the chip to the rack level. And since rack door cooling is included in the rack, I just wanted to note that putting heat rejection at the back of an equipment rack can be fantastic. It can really improve the density at which you're able to deploy computation. So you can put 30 kW a rack in a system that has a heat rejection rear door. So the great thing about those is that it's really simple. Those heat rejection doors, it's really just a bunch of fans that pull the server heat through some coils and then lets it out into the rest of the room. And the rest of the room in that condition is comfortable. It's like 70 degrees or whatever is the inlet target for that type of rack. And it's close coupled, so there's not that much leakage through the rack. It does work really well. I was just in a data center that had rear door heat rejection, and it's just so nice to be there compared to a lot of types, especially hot aisle containment. Hot aisle containment is torture if you're trying to do work in the hot aisle, because good hot aisle containment is going to be 100 degrees, and it sucks. It sucks to be doing cabling in an 100-degree space. So putting that heat rejection so close to the servers is another good way of doing heat rejection. Now, that's still pretty difficult because you have to have a lot of connections, and you have to have flexible connections to each one of those rack doors. And there's different technologies on it. I won't go into all that, but it's a pretty good solution, especially if you have high density in your data center.
Immersion cooling.
Okay, last but certainly not least is immersion cooling. Immersion cooling, I talked about last week with Daniel Pope. I think it is a fantastic technology that's probably about ready for prime time. The idea that you can take a server and just dip it in a dielectric fluid like an oil or another heat rejection medium, it means that you don't have to worry about air at all. The fluids that you would be using have heat capacity that might not be as good as water, so it might not be able to carry as much heat per unit volume as water, but they can still handle a lot of heat per unit volume, like a whole lot. I think mineral oil is somewhere around 2/3 as good as water. And what that enables you to do is shrink your racks, put more stuff in the same area. And, so having an immersion cooled rack can be smaller, but also if you were to design the server around immersion cooling, you can take a lot of the components that would be quite large and shrink them down. You can take heat sinks that would be quite large and make them smaller. You can take some of the size of the printed circuit board and make it smaller because you don't have to worry about making room for that big heatsink. You can couple your hard drives directly to your printed circuit boards. You can couple your memory much closer to your printed circuit boards. You can almost make the PCB flat. The whole server could, instead of taking up 1 U, could take up a half a U. Or if you have blades, instead of taking up a 1-inch form factor, they could take up a 1/2-inch form factor. It's just possible to really simplify and tighten up all of those distances. And like we were saying before, that enables you to reduce the total amount of resistance and really improve the electrical efficiency of the whole server and whole system. So the more that systems are designed for immersion cooling, the more that those benefits will become available to everyone. That it won't just be the giant hyperscale customers that are able to get those efficiencies. It can be anyone who has bought into the immersion cooling concept. Problem with immersion cooling is that not many servers are built that way at the moment. There are very few servers that have 2 kW in a 1 U form factor. It's growing. Densities are really increasing very quickly. It's funny, I went to a conference a few years ago, and the topic was how colocation doesn't need high density because people have been threatening to have high density for many, many years, and it never happened. Well, the next year, there was this huge clamoring for GPUs because of blockchain, and they were not able to provide it. I could not be more on the bandwagon of increased density and very, very high density because of all the reasons that I've already stated. I really hope that we start pressuring server manufacturers to build their units in such a way that they can handle that ultra high density, so that you can have the same economies of scale at the hyperscale as you do at a small mini node data center. It's possible, it's available. I think it would make the world a better place, but it's going to take time to get there. I know a lot of people are working on this. I am very thankful to the Open Compute Project for pushing this, but there's still some way to go. That's our show. I'd like to thank the Open Compute Project for providing all of the materials that I used for putting this episode together. It's a very, very valuable resource, and I really want people to take a look at it. You can go to opencompute.org for more details. I'd like to thank Greenlane Design for sponsoring this episode. Please go to their website, ask for an evaluation, and mention the podcast. Also, please make sure that you follow us on Twitter. Our Twitter handle is data_good. You can find me on LinkedIn. Just search for my name. And we'll talk to you next time on the podcast.